Okay, this is AP Calculus AB, and in this lesson, I am going to talk about section 4.1 in your textbooks, which is the chain rule. This is really the start of our fourth unit, and before I jump into this, what I wanted to warn you about is that this is where we make a big change in this course from everything being relatively easy from a derivative standpoint to things being much, much more complex. And you'll see what I mean as I go through some of the examples in this lesson. When we start bringing the chain rule into play, not only are we starting to deal with more difficult functions, but the algebra involved to solve out our derivatives and get them into a simplified form is going to increase by a pretty large multiple. So what you'll notice here is the idea of the chain rule, once you have a grasp of it, is not that difficult, but the algebra that you have to do after you apply the chain rule sometimes can be pretty extensive. Okay, so let me start by showing you an example where we can apply the chain rule in a way that lets you see it sort of side by side with the methods that we've used up to this point. So what I've got here is a function y equals 3x squared plus 1, that quantity is squared. And what we're trying to do is take the derivative of it. Now, one way to do this would be just square that expression. So FOIL it out, figure out what the expression is, and take the derivative term by term. That works when we have an exponent like a 2. But let's say we had the same situation and this was 3x squared plus 1 raised to the 6th power. Well, expanding that out now is not quite so simple. So I'm going to show you a simple one where we can do it both ways so you can see side by side the methods that we've been using up to this point, and then the chain rule really result in the same thing. So when we use the chain rule, we're really essentially treating everything as a composite function, and that's what's being done here. Now, I will tell you in advance, this is going to look like the chain rule is really difficult because I'm going to show you this in a long, drawn-out way. There is a shortcut for the chain rule that we're going to go through in a couple of minutes that will make this process much, much more streamlined, and you won't have to write down nearly as much as what I have here. But what we're doing here is we're rewriting this function as a composite function by thinking of sort of an outside function and an inside function. We're thinking of it in that sense. So we're saying y is equal to u squared, where u is equal to 3x squared plus 1. Now, taking the derivatives of those two pieces, that would be relatively easy. So dy du is 2u. Notice we took the derivative here in terms of u because we had y in terms of u. And then we have du dx is equal to 6x. Now, neither one of those is what we're looking for. We're looking for dy dx. But if we do a little bit of differential math, which we haven't really talked about yet, but differentials are just like variables. We can work with them in the same way. So notice this statement here. This is sort of the key to the chain rule. dy du multiplied to du dx. Think about what would happen here. These differentials are just essentially can be treated as variables when we're thinking of it from the, I guess, the math standpoint of how do you work with differentials. So du cancels out, and then if I multiply dy du times du dx, that simplifies down to du dx. Okay, so in the end then, if I substitute my dy du and my du dx back in, I get 2u times 6x. And now remember, u was 3x squared plus 1. So I can substitute in that 3x squared plus 1. And now I've got my derivative in terms of x. And if I simplify that down, I have 36x cubed plus 12x. Okay, so that's really the chain rule. We're sort of thinking of it as an outside function and an inside function. Now, if we had done this the other way that I mentioned at the beginning, if we had expanded this out, here's what we would have had: 9x to the 4th plus 6x squared plus 1. Take the derivative, we get 36x cubed plus 12x. So both of those results are the same, even though we went about it in a different way. Now, it does seem like the chain rule is a lot more work, and in this case, it actually was. But typically, if we use the chain rule, it's going to save us a lot of steps. And even on this problem, if I didn't go through the chain rule in the long way, you would see that the chain rule would be pretty quick and almost just as fast as foiling this out and taking the derivative. Okay, so let's take a look at another example. So we have dy dx for y is equal to sine of 3x squared plus 5x. So we're trying to find that derivative. Now, rather than writing out everything with the u and going through that whole process this time, I want to show you this in the streamlined version. We're still going to think of this in the same way. We have an outside function and an inside function. The outside function would be the sine. The inside function would be the 3x squared plus 5x. So when I do my derivative here, or take my derivative, now I'm going to work from the outside in when I do the chain rule. So the derivative of sine is cosine. So I would have the cosine of 3x squared plus 5x times the derivative of the inside. Well, the inside is the 3x squared plus 5x. So what I'm going to multiply by is the derivative of 3x squared plus 5x, which would be 6x plus 5. So in the end, really, I've done my derivative in one step. I would probably write this in a different order just to make it really clear that the 6x plus 5 is multiplying to the cosine. But there's really not a lot to the process of using the chain rule once you know how to do it. Now, that one might not make total sense to you because I skipped over what I did previously, but the main thing is you take the derivative of the outside times the derivative of the inside. There can be more layers to your function, and we'll get into some problems like that later on where there's more layers to it, but we just always work from the outside in is the main idea. Okay, we can also look at the chain rule from a function notation standpoint. If I take the derivative of some function of u, so that's what this is saying, then it's the derivative of the outside times the derivative of the inside. F prime of u times du dx. So still the same thing, just written in a slightly different form. So here's an example of that. The derivative of the sine of 6x. Well, the derivative of sine is cosine. So I have cosine 6x times the 6. And again, I would probably write this as 6 cosine 6x, just to make it clear that the 6 is multiplying to the cosine. It's not going to be 36x. Okay, so we can also see the chain rule in a composite notation using this form where we have f of g of x. If I take the derivative of f of g of x, f of g prime of x would be f prime, because that would be my outside function, of g of x times g prime of x. Again, working from the outside in. Okay, so let's take a look at some examples here. This one has more layers to it. So when you have more layers, you have to be careful with this. So notice we have the sine of 5x squared here. I'm going to write this in a slightly different form just to make it really clear that I've got the sine of 5x. That quantity is being squared. Okay, so now that I see it that way, when I take the derivative, we're going to work from the outside in. Start with your power rule, which would be the 2. So 2 times the sine of x, now, or sine of 5x, now raised to the first power. Now working in, now I'm going to multiply to the cosine of 5x. And let's see here. Kind of running out of space here a little bit. So cosine of 5x times the derivative of 5x. So we really have 3 layers. We have the power rule layer, we have the trig function layer, and then we have the 5x. In the end, what I end up with here is 10 times the sine of 5x times the cosine of 5x. Okay, so not that difficult to do, but you do definitely have to sort of think through the process of what's the outside part of my function and work my way in. So here's the other form of the chain rule that we looked at the beginning. You can write the chain rule in function notation. You can write it in the differential notation. They all mean the same thing, which is the derivative of the outside times the derivative of the inside. All right, so I'm going to go through a couple of these examples with you, but a lot of what the rest of this is going to be is practice problems. So I'm going to show you 2 or 3 of these, and then I'm going to have you pause the video and try a bunch of these for practice, and then you'll unpause the video and check answers. But let me show you the first few of these. We have x squared cubed. Now I put this one in here because there's 2 ways to look at this problem. One way you could do this is you could say, oh, well, this is x to the 6th, so dy dx would be equal to 6x to the 5th, just using the power rule. But I want to show you this with the chain rule. We could also take the derivative in the original form. Well, in the original form, what's on the outside is the power of 3. So I'd have 3 times x squared quantity squared, times the derivative of the inside. Derivative of x squared is 2x. And then notice what we end up with here, which is 6x to the fifth. So again, I did that two different ways. I probably would actually do that in the first way, or the first method, but the second method gave me the same result. So we don't have to use the chain rule always just because it's available to us, but there are a lot of cases where we would choose to use the chain rule. And the next one's a good example of that. We have 4x squared minus 7 raised to the fifth power. Now, if you remember your binomial expansion from Algebra 2, you might know how to expand this thing out and get a bunch of terms. That's really not the best way for us to go about it for a couple of reasons. First of all, it's a lot of extra algebra. But the second reason is when we get our derivative, when possible, we like to have it in a factored form for when we get into our applications of derivatives. So what I would prefer here is to use my chain rule. And that's what I'm going to do. When I take the derivative of this, obviously the power of 5 is on the outside. So 5 times 4x squared minus 7 now raised to the fourth power times the derivative of the inside, which is 8x. And there's my derivative, and I would probably write this out as 40x times 4x squared minus 7 raised to the fourth power. So again, the advantage to this is I have this in a factored form. And I've mentioned this a couple of times before. When we get further along with the derivatives, we're going to start to want to know when is the derivative equal to 0 and when is the derivative undefined. Well, if I set that derivative equal to 0, it's really easy to see where the derivative is 0. If I had it in an expanded form, it would be very difficult to figure out where the points were that the derivative was 0. Okay, so keep that in mind when you're trying to decide how do you want to simplify. Try to think about what we're going to do next, which is set the derivative equal to 0 and try to figure out those points. Okay, so let me show you one more of these, and then I'll have you try a bunch of these on your own. So the next problem we have here is 5 minus 3x cubed, and we're taking the square root of that. So when you're using the chain rule, you're probably going to want to rewrite this in this form. 5 minus 3x cubed raised to the 1/2 power. Both of those function notations mean the exact same thing, but it makes it a little bit more obvious what to do here. So when I take my derivative, I'm going to start with what's on the outside, the 1/2. Now 5 minus 3x cubed raised to the negative 1/2 power times the derivative of the inside, which would be negative 9x squared. And there's my derivative. Now, that's not a very good form to have my derivative in because I have that negative exponent, but that is my derivative. So at this point, I'm just doing a little bit of algebra. And what I'd end up with is negative 9x squared over 2 times the square root of 5 minus 3x cubed. Okay, so again, it's easy to see where that derivative would be 0. It's easy to see where it's undefined based on the form that I have it in. Okay, so go ahead and finish the rest of these example problems up until you get to the page with the table, this page here. So there's a couple pages of examples here. It looks like you've got probably 10 or so for practice. And then after you have finished a bunch of them, unpause the video, check your answers, and then I'll show you that last type of problem. Okay, and here are the answers you should have ended up with for the rest of these. We have x over the square root of 1 plus x squared. So I chose, rather than using the quotient rule combined with the chain rule, I chose to rewrite this as x times 1 plus x squared to the negative 1/2 power. You could do it that way. And I guess actually in the way I worked it out here, I went ahead and worked it out with the quotient rule. But either way is going to result in the same answer. But you notice here right away, these can start to get pretty messy algebraically. In terms of the derivative, here's my derivative using my quotient rule. So I did the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared. Don't forget about your chain rule here. This 2x came from the chain rule when I took the derivative of the denominator. Now, that's my derivative. What I have circled there, that is technically the derivative. So everything I do from this point on is going to be algebra to simplify my solution down. That's not really a nice derivative to work with. If I have to plug a value into it, if I need to get a second derivative, if I need to do anything with that derivative, it's going to be pretty messy. So what we do at this point is try to simplify it out. First thing I did was rewrite this so that I don't have a negative exponent. And you can see now I've got this complex fraction. I didn't show all the steps here, but now I would get a common denominator within the terms of my numerator or with the terms in my numerator. And then everything will simplify down into this form. So when you're working through these problems, and let's say you're doing it in Math Excel, or you got a question on the test, or whatever it is, this is the form I want you to be shooting for. When you are working on a multiple choice question, it would be pretty obvious. If you got this as your first step and you looked at the answer choices, they're not going to look like that. They're definitely not going to look like that. But even if it's free response, I always want you to try to simplify it down as much as you can. So keep that in mind. All right, so the next one here, notice that we're using a few derivative rules. We have x cubed times 2x minus 5 raised to the fourth power. So we're going to have the product rule here. We're going to have the chain rule. We're going to have the power rule. So we've got three different derivative rules within the same problem. And this is another one where the first step is fairly simple. This is the only step that I'm actually doing calculus. Right here, I took the derivative using my product rule combined with my power rule and my chain rule. At that point, I want to get this into a simplified form. So what I did was I noticed that there was a 2x minus 5 cubed in both of those expressions. So I factored that out. I also noticed there was an x squared in both of those expressions. And when I factored everything out, what I was left with is this nice factored form. Okay, so again, the derivative is typically the easy part on the chain rule. Getting it all simplified down, that's where it can get a little bit messy. All right, let's look at the next one. Tangent 4x. Eventually, I want you to get to the point where on most of these, you just skip over the extra steps. And this is a good example of one where you can easily skip the steps. The derivative of tangent is secant squared. The derivative of 4x is 4. Okay, same thing on this next one. Cosine of t squared plus 1. Derivative of cosine is negative sine. So I have negative sine t squared plus 1 times the derivative of t squared, which is 2t. Here we've got sine of x raised to the negative fifth power. So I'm just doing the power rule combined with the chain rule. So I brought the negative 5 down, sine x to the negative 6 times cosine. And now it's just a matter of which form do I want to have my answer in. Typically, we don't want negative exponents. So either of these two answers would be acceptable. And it really depends on what we're going to do next with our problem if we were going to do something more with this derivative. All right, now we've got sine x times the tangent of 4x. And for this one, you can see that I did the product rule. And then just don't forget to do the chain rule when you take the derivative of that tangent 4x, when you do that within your product rule. Okay, the next one here, this one's got a few layers to it. We have 1 plus cosine squared 7x raised to the third power. So notice that I had to essentially go through 4 layers here. So what's on the outside is this 3. So I did that first. I did the power rule. You can see I've got the 3 down. Now I have that whole expression squared. Now I'm going to take the derivative of what's inside. Well, the derivative of 1 is 0, but now I have to deal with this power rule. Brought the 2 down. Now I have cosine raised to the first power. Now the derivative of cosine is negative sine, and then the derivative of 7x is 7. Okay, so this one's a good example of how you can check to make sure that you haven't forgotten anything. If you go through one of these problems with the chain rule, you should have accounted for the derivative of all of the parts of your function. And you can see here I dealt with every single piece, both of those power rule pieces, the derivative of the trig function and the derivative of the 7x. And then also notice I can simplify this just a little bit by multiplying those constant values out. And that's what I end up with as my factored solution. Okay, this one is t times the cosine of pi minus 4t. The only difference here is we have everything in terms of t. We're going to take the derivative with respect to t, but it's just a product rule question. Don't forget to do your chain rule and include that negative 4 there at the end, because pi minus 4t, when I take the derivative, I'm going to get negative 4. But in the end, not that difficult compared to some of the ones we've gone through at this point. This one, we've got tangent of 5 minus sine 2t. So the derivative of tangent is secant squared. The derivative of the 5 minus sine 2t, that's where this part of it came from. The derivative of sine is cosine. The derivative of 2t is 2. Okay, and let's take a look at a couple more here. We've got this r is equal to 2 theta times the square root of secant theta. So when it says r prime, I have to assume that I'm taking the derivative with respect to theta because r is dependent on theta, the way that this equation is written. So this one's a little messier, but it's still the same process. You can see that I did my product rule here. So derivative of theta was 1, so 2 times the square root of secant theta. And then this is where I got into all of the chain rule part of it. When you get to this point, you might get this answer and feel like, okay, I'm done. And that would be an okay answer. If this were a multiple choice question, though, it would probably be simplified a little more. And so what happened in these next steps is just essentially getting a common denominator. And what I did was I multiplied on the second expression, I multiplied by square root of secant theta over square root of secant theta. And the reason I did that is I knew that a secant theta would cancel. And then I could get this into an expression that I no longer have a denominator. All right, this one's just y double prime, second derivative. So we've seen that notation before. Just notice that the chain rule comes into play on both of those when you take the derivative. And then here's an example of the same types of problems that we've been doing, but now instead of using the quotient rule, I chose to do this with the chain rule. So 1 over 1 minus 2x quantity cubed. And really, I would be using the chain rule either way, but the chain rule allows me to simplify this a little bit. So what I did was I rewrote the function as 1 minus 2x to the negative 3 power. And now I'm going to take the derivative with the chain rule from there, and I end up with this as my derivative. Now, if you tried to do that with the quotient rule, which you may have, you'll end up with the same result, but you'll notice that you do get a little bit messier algebra as a result. Okay, that should actually be a positive for there. Okay, and then when you plug 1 into that, you can see that you get a value of 6. All right, so the last thing I wanted to show you here is a special type of problem. And this is one that tends to show up a lot when we're dealing with the chain rule. And so some of these, I'm just going to give you the solution because you know how to do some of these. So the derivative of 2 f of x at x is 2. Notice we have f, g, f prime, and g prime defined for different x values. So when you take the derivatives of these, some of these are relatively simple. This one you would get 2/3. This one you would get 2 pi plus 5. And you've seen some questions like this already. F times g, it's just product rule. You would get 15 minus 8 pi. And then f of x over g of x would just give me 37 over 6 if you use your quotient rule. But let me show you one of the chain rule questions. So we have f of g of x at x is equal to 2. Now, what we're doing here is we're sort of taking all of the extra stuff out of the problem, all that extra algebra that we have to do to simplify down. We're eliminating all of that by just using this general function notation. So they want us to find the derivative of f of g of x at x is equal to 2. If I take the derivative here, remember, it's just working from the outside in, I would have f prime of g of x times g prime of x. Okay, now I want to evaluate that at the point where x is equal to 2. So if I evaluate that at x is equal to 2, I'm going to get f prime at g of 2 times g prime at 2. And now I just have to pull the values out of the table. And g of 2, if you go back to that table, g of 2 would be equal to 2. So this is essentially f prime of 2. G prime at 2 was negative 3, so this is times negative 3. And then if I look back at my table, f prime at 2 is 1/3. So 1/3 times negative 3 gives me negative 1. And that would be my solution. Now, these are not necessarily hard questions, but they're really easy to mess up. And what's easy to mess up about them is when you start looking at the values in the table, try not to rush through it, because you've got to be really careful that you're looking at the points where x is 2 in this case, and not where x is 3. So make sure you're in the correct row and the correct column before you start picking values out. Let me just show you one more derivative. I'm not going to show you the whole problem, but this next one we have the square root of f of x. So remember, that's essentially f of x raised to the 1/2 power. So if I were to take the derivative of that with respect to x, what I would get, first I would do my power rule, 1/2 now times f of x raised to the negative 1/2 power. And the thing that people tend to forget about this is the chain rule. Remember that the exponent of 1/2 was on the outside. The derivative of the inside is f prime of x. Okay, and then we have to go through and do the same process. Evaluate this when x is equal to 2, and you can go through and plug in the values and simplify down, and this one actually turns out to be 1 over 12 root 2. Okay, so there's 2 more or 3 more here, and you could just take a minute, and I want you to try these last 3. So just pause the video, try these out, and then when you unpause it, I'll show you the solutions. Okay, so for these last few problems, first of all, for g, we get 5 over 32. Remember, that's just g of x to the negative 2 power. Don't forget your chain rule. H is a little bit messy, but it's the same thing. We have all of that raised to the 1/2 power. So we have to make sure we use our chain rule when we go through the process, but there's the result you should have gotten, negative 5 over 3 root 17. And on the last one, I, when you take the derivative, you're going to end up needing g prime at 10. Well, the problem is we don't have information about g prime at 10. So for us, this is not possible to solve. We don't have enough information. And sometimes you'll come across problems like that. It'll say solve the problem if possible, if not, state what you're missing. In this case, I would just say this is not possible because I need g prime at 10. All right, so make sure you practice a lot with this. Try to really do a good job with simplifying your algebra or your algebraic expressions down so that they're in a form, like I mentioned before, where you can easily see where the derivative is 0 or undefined.